Have you ever gazed up at the night sky, letting your eyes wander among those countless stars, and suddenly felt a dizzying thought creep in? What if space never ends? What if, no matter how far we travel, the universe just keeps stretching into infinity? It's a question that's haunted humanity for centuries, sparking debates among scientists, philosophers, and dreamers alike. And here's the wild part: we still don't have a definitive answer. Some researchers argue the cosmos is boundless, an endless expanse where galaxies stretch on forever. Others believe it's just so colossally big that, to us, it might seem infinite, like standing on the shore of an ocean, so vast you'd swear there's no other side. So, which is it? Is the universe truly infinite, or is it just so mind-bogglingly large that our brains can't even begin to comprehend its scale? Think about it this way: if you could board a spaceship and fly in one direction at the speed of light for billions of years, would you eventually hit some kind of cosmic wall? Or would you just keep going forever? The answer isn't just about satisfying curiosity, it reshapes how we understand reality itself. From the fabric of spacetime to the possibility of parallel universes lurking beyond our sight, this question cracks open doors to some of the most thrilling mysteries in science. And that's exactly where we're headed. Over this journey, we'll dive into cutting-edge theories about cosmic horizons, the startling clues hidden in the afterglow of the Big Bang, and even the brain-bending idea that our universe might be just one bubble in an infinite multiverse. You'll hear why some of the brightest minds in physics passionately disagree on this, because when it comes to infinity, even the rules of reality seem to bend. So buckle up. By the end of this, the night sky will never look the same to you again. But what does it really mean for the universe to be infinite versus just unimaginably large? Let's strip away the sci-fi dazzle for a moment. Infinity isn't just a fancy word for really big, it's a radical concept. A truly infinite universe has no edges, no boundaries, no matter how far you travel. Picture an endless treadmill. No matter how fast or long you run, you're never closer to finishing because there's no finish line. Now contrast that with a very big universe, one that's finite but expanding, like a marathon where the race course itself keeps stretching as you run. You might never reach the end, not because it doesn't exist, but because it's always moving farther away. This distinction isn't just philosophical wordplay. Ancient thinkers like Aristotle wrestled with it too, arguing over whether the cosmos had edges or stretched on forever. Fast forward to today, and modern cosmologists face the same puzzle, but with way better tools. Telescopes peer billions of light years into space, mapping galaxies like cosmic breadcrumbs. The kicker: everything we see suggests the universe is at least so vast that its full scale might forever lie beyond our reach. But vast doesn't necessarily mean infinite. Here's where things get juicy. If the universe is finite, what shape does it take? Some theories suggest it could curve back on itself like a four-dimensional balloon, travel far enough in one direction, and you'd loop back to where you started, though don't pack your bags for that trip yet. It'd still take trillions of years. Others propose wilder ideas, like our universe being a single bubble in an endless multiverse foam. Meanwhile, the infinite cosmos camp points to math and physics that don't require an edge to make sense, just an endless sea of spacetime where galaxies fade into the distance forever. So why hasn't science settled this? Because infinity is notoriously slippery to prove or disprove. You can't measure what has no end, and even a finite universe might be so colossal that its edges are effectively invisible to us. It's like trying to find the walls of a room when you're standing in the dead center of a stadium the size of a galaxy. All we know for sure, however big or boundless the universe truly is, one thing's certain: it's got plenty of room left to surprise us. Right now, the most we can say for certain about the size of our universe comes down to what we can see, and even that is staggering. Picture holding a flashlight in a thick fog. The beam cuts through, illuminating only what's within its reach, while everything beyond remains shrouded in darkness. That's essentially our cosmic predicament. The observable universe, the sliver of space we can detect, spans an almost inconceivable 93 billion light-years across. But here's the twist: that number isn't just about distance. It's a time capsule. Every photon of light that reaches us is a messenger from the past, some traveling for billions of years before finally hitting our telescopes. And because the universe has been expanding all that time, the sources of that light are now much farther away than when they first sent it. Think of it like a cosmic breadcrumb trail, except the trail keeps stretching as you follow it. But here's where it gets mind-blowing. Even within this observable bubble, most of what's out there is already lost to us forever. Thanks to the relentless expansion of space, 94% of the galaxies we can theoretically observe are now unreachable. Their light hasn't reached us yet, and because the universe is accelerating outward, it never will. They're racing away faster than light can bridge the gap, like letters mailed across an ocean, only for the ocean itself to grow faster than the mailboat can sail. This cosmic horizon isn't just a limit, it's a one-way barrier locking away entire swaths of the universe from our view. So what does that mean for infinity? Well, if the observable universe is this colossal, and still just a tiny fraction of whatever lies beyond, then the true scale of everything could be far grander than we've dared to guess. Or it could mean we're trapped in a cosmic fishbowl, forever wondering what's outside the glass. Either way, one thing's clear: the universe isn't just big. It's hungry. It devours distances faster than light can cross them, leaving us with a humbling truth: we may never know just how much we're missing. The story of cosmic expansion begins with a puzzle, one that astronomer Edwin Hubble cracked open in the 1920s. While studying distant galaxies, he noticed something bizarre. Their light wasn't just dimmer the farther away they were, it was shifted. Imagine a fire truck siren. As it races away from you, the sound stretches into a lower pitch. That's the Doppler effect in action. Hubble saw the same thing happening with starlight. The light from these galaxies was stretched toward the red end of the spectrum, as if the universe itself were tugging space apart between us and them. That redshift wasn't just a quirk. It was evidence the cosmos wasn't static. The fabric of reality was stretching, carrying galaxies along like raisins in an expanding loaf of bread. This revelation turned cosmology on its head. If space was stretching, then rewinding the tape meant everything had to have been squished together at some point, a single, unimaginably dense speck. That's the Big Bang, but here's the twist. It wasn't an explosion in space like fireworks scattering debris. It was space itself unfurling, a cosmic zoom lens pulling the entire universe wider with every passing moment. Picture a balloon inflating, not with dots on its surface flying outward, but with the rubber itself stretching, making the dots drift apart. That's why no matter where you are in the universe, it seems like everything's moving away from you. There's no center, no edge, just the relentless stretch of space-time itself. Now, here's where the real mystery kicks in. If the universe is finite, if it's not infinite but instead some colossal yet bounded expanse, then what lies beyond its edges? Saying nothing doesn't cut it. Nothing isn't a concept our brains can even process. Maybe it's other universes bubbling in some grand multiverse foam. Or perhaps our universe loops back on itself, like a cosmic Pac-Man screen where traveling far enough in one direction brings you back to where you started. But here's the catch: if it is infinite, then outside might not even mean anything at all. Infinity doesn't have edges, it just is, so which is it? The chilling truth is, we might never know for sure. The universe could be playing the ultimate magic trick, expanding so fast that any clues about its true shape are forever out of reach. And that's the real cliffhanger. Whether it's finite or infinite, one thing's certain: the cosmos is far stranger, far more alive than we ever imagined. And the next chapter, well, it's written in the darkness beyond the reach of our telescopes. If the universe isn't infinite, what shape does it take? One of the most fascinating ideas is the closed universe, a cosmos that curves back on itself like the surface of a globe, but in 3 dimensions. Picture a video game where, if you walk far enough to the right, you eventually reappear on the left. Now imagine that in real life, but with galaxies. Fly straight long enough in one direction, and you might just end up back where you started. It's a mind-bending concept, but one that's rooted in Einstein's theory of general relativity. Space itself could be warped by gravity, bending into a kind of 4-dimensional sphere where there's no edge, no boundary, just an endless cosmic loop. But the closed universe isn't the only finite possibility. Some theorists propose an even wilder shape, the torus or donut model. Here, space isn't just curved, it's twisted. Think of a classic arcade game like Asteroids, where shooting off the top of the screen brings you back in at the bottom, and exiting left pops you in on the right. Now scale that up to universal proportions. In a torus-shaped cosmos, you could theoretically aim a spaceship in one direction, travel for trillions of years, and eventually return to your starting point just from a different angle. It's like the universe is a cosmic Möbius strip where paths twist in ways that defy our everyday intuition. Einstein himself wrestled with these ideas. Early in his career, he struggled to reconcile his equations with the notion of a finite universe. The math kept suggesting the cosmos might curve back on itself, but the idea felt philosophically unsettling. How could space have no edge? What would lie outside? It took years for even him to accept that the universe might not need an edge to make sense, that infinity wasn't the only way to avoid boundaries. Instead, it could fold in on itself, creating a self-contained reality where the question, what's beyond, simply doesn't apply. Yet here's the catch, proving any of this is staggeringly hard. For a closed or torus-shaped universe to work, the curvature of space would have to be extreme enough to create these loops. But so far, our most precise measurements suggest space is very nearly flat. Like standing on a beach and trying to spot the curve of the Earth, the bend might be too subtle to detect. That doesn't mean these models are wrong, just that the universe might be so vast, its true shape exists on scales we can't yet observe. And that's the real punchline. Whether it's a cosmic sphere, a twisted donut, or something even stranger, the shape of the universe isn't just a trivia question. It's a clue to the deepest laws of reality. If space curves, what does that say about gravity's grip on the cosmos? If it loops, could there be echoes of ancient light circling back to us? Every hypothesis opens new doors and reminds us that in the grand puzzle of existence, some pieces might always lie just beyond our reach. Now let's flip the script and consider the opposite possibility. What if the universe is infinite, not just vast but truly boundless, with no edges, no curves, and no end to the galaxies streaming endlessly into the darkness? This is the heart of the flat and open universe models, where space stretches forever without looping back on itself. Picture an infinite sheet of graph paper, its grid lines extending in all directions without warping or bending. That's the essence of a flat universe. No matter how far you travel, space remains stubbornly, perfectly even. And the wildest part, this isn't just sci-fi speculation. The math of Einstein's relativity allows for it, and our best measurements of cosmic microwave background radiation, the afterglow of the Big Bang, hint that the universe might indeed be astonishingly flat. But flatness isn't the only flavor of infinity. Enter the open universe model, where space isn't just infinite, it's negatively curved, like a cosmic saddle stretching eternally outward. Here, parallel lines would gradually diverge, and the angles of a triangle would add up to less than 180 degrees. It's a universe that refuses to close in on itself, forever expanding at an accelerating pace. And while that might sound abstract, it has real consequences. In an open universe, gravity's grip weakens over time, leaving galaxies to drift apart until they're lost in an ever-darkening void. Now, here's where things get truly surreal. If the universe is infinite, then quantum mechanics suggests something extraordinary: endless repetitions of you, me, and everything else. In an infinite cosmos, every possible configuration of matter must repeat somewhere, meaning there are statistically countless versions of Earth, each with subtle or staggering differences. Somewhere out there, a version of you is reading these words in a universe where dinosaurs never went extinct or where gravity is twice as strong. It's not magic, it's just the inevitable outcome of infinity. Stephen Hawking once captured this elegantly: the universe has no edge in space or time. No boundary means no need for a creator or a starting point. The cosmos could simply be self-contained and self-explanatory, with quantum fluctuations birthing new big bangs eternally. Imagine a cosmic foam where universes bubble up endlessly, each with its own laws of physics, its own version of reality. Our universe might just be one accidental masterpiece in an infinite gallery. Yet for all its grandeur, infinity comes with a haunting caveat. If the universe has no edge, then everything we'll ever see, every star, every galaxy, is just a speck in an ocean without shores. We're left with a humbling truth: even if the cosmos is infinite, we'll only ever know our tiny corner of it, the rest forever beyond our reach, glittering in the dark. To understand the true shape of the universe, scientists turn to the oldest light in existence, the cosmic microwave background. This faint glow is the remnant heat from the Big Bang, a snapshot of the infant cosmos when it was just 380,000 years old. Like finding fingerprints on a piece of ancient pottery, researchers study the patterns in this light for clues about the geometry of space itself. The logic is elegant. If the universe is curved, the paths of those primordial photons would bend as they traveled across the cosmos, leaving telltale distortions in the temperature fluctuations we observe today. Take a flat universe first. In this scenario, space behaves like a vast, unending sheet of paper. Parallel light rays stay parallel forever, and the angles of a triangle add up to exactly 180 degrees. When cosmologists analyzed data from NASA's Wilkinson Microwave Anisotropy Probe, or WMAP, they found something striking. The temperature variations in the cosmic microwave background matched a flat universe with astonishing precision. The measurements were so exact, they ruled out significant curvature with 99.9% confidence. It's like tossing a handful of marbles onto a table and watching them roll perfectly straight, never veering toward or away from each other. No hidden slopes, no unseen dips. But what if the universe isn't flat? A spherical or closed cosmos would curve gently like the surface of a balloon. Light rays that started out parallel would eventually converge, the way longitude lines meet at Earth's poles. Here, triangles bulge, their angles adding up to more than 180 degrees. If this were true, the cosmic microwave background would show hotter or colder spots appearing larger than expected, as if space itself were magnifying them. Yet WMAP saw no such distortion. The patterns were too crisp, too mathematically tidy to fit a spherical model. Then there's the hyperbolic or saddle-shaped universe, a mind-bending scenario where space curves negatively, splaying outward like a trumpet's bell. In this wild landscape, parallel light rays diverge and triangles shrink, their angles summing to less than 180 degrees. The cosmic microwave background in such a cosmos would look stretched, with hot and cold spots appearing smaller and more fragmented than in a flat universe. But once again, the data didn't align. The WMAP results and later, even sharper readings from the Planck satellite painted a clear picture. Within the margin of error, our universe is flat. Here's the caveat, though. These measurements only confirm flatness within the observable universe. Beyond our cosmic horizon, space could theoretically curve in ways we can't detect. Imagine standing in the middle of an ocean so vast you can't see land. The water might seem flat as far as your eyes can tell, but that doesn't mean the entire planet lacks curvature. Similarly, our universe could be so colossal that any curvature is simply too subtle to measure with today's tools. That's why flatness doesn't necessarily mean infinity. A finite universe could still appear flat if it's big enough, like how a basketball feels smooth under your palm despite being part of a sphere. Some theorists even speculate about exotic topologies where a flat universe wraps around itself in higher dimensions, like a video game screen that teleports you from one edge to the other. But for now, the simplest interpretation, the one that fits all the data without extra assumptions, is that space stretches on, uncurved and possibly endless. What's remarkable is how much rides on this deceptively simple question. A flat, infinite universe implies a cosmos where the rules of physics play out the same everywhere forever. It suggests that somewhere beyond the reach of our telescopes, the same laws of chemistry, the same dance of particles, the same potential for life might repeat endlessly in the dark. Or it could mean we're floating in a raindrop of space-time so vast, its true shape remains just out of sight. Either way, the cosmic microwave background isn't just ancient light, it's a mirror reflecting the deepest structure of reality back at us. What if our universe isn't alone, not just in the sense of distant galaxies, but as one of countless cosmic siblings, each with its own unique rules, its own version of reality? This is the spine-tingling premise of the multiverse. Start with the simplest version, the level 1 multiverse. If space truly is infinite, then somewhere out there, every possible arrangement of particles must repeat. Picture shuffling a deck of cards forever. Eventually, you'll get the same order twice. Now scale that up to atoms, planets, and even people. In an infinite cosmos, there's a version of Earth where your morning coffee tasted slightly better, where dinosaurs still roam, or where gravity itself behaves differently. It's not science fiction, it's statistics. Infinite space guarantees infinite possibilities, but that's just the beginning. Enter level 2, bubble universes. Imagine a cosmic bubble bath, where each frothy sphere is its own self-contained universe, floating in an unfathomably vast foam. These bubbles aren't just distant regions of space, they're entirely separate realities, each born from its own Big Bang, each with its own fundamental constants. In one bubble, gravity might be 10 times stronger, crushing stars into black holes before life can form. In another, electrons might be heavier, preventing atoms from bonding at all. This isn't wild speculation. It emerges naturally from theories like eternal inflation, where the fabric of spacetime expands exponentially, spawning new universes like buds on a never-ending vine. Then there's Max Tegmark's mathematical universe hypothesis, a radical idea that pushes the boundaries of imagination. Tegmark suggests that reality isn't just described by math, it is math. Every possible mathematical structure exists as a physical universe somewhere in the multiverse. Think of it like this: the number 4 doesn't just represent 4 apples, it is a universe unto itself with its own rules and dimensions. Critics call it philosophy disguised as physics, but Tegmark argues it's the ultimate testable hypothesis. If a theory predicts observable patterns in our universe, then its mathematical siblings must exist too. So how do we reconcile these dizzying ideas? The level 1 multiverse is almost inevitable if space is infinite. Level 2 emerges from the math of cosmic inflation. And Tegmark's vision, that's where the line between physics and metaphysics blurs. But here's the kicker: these theories aren't mutually exclusive. Our universe could be one bubble in an endless foam, floating in an infinite mathematical ocean. And somewhere in that ocean, another version of you might be reading these words, wondering the exact same thing. The multiverse isn't just about multiple worlds, it's about multiple realities, each playing by different rules. Whether it's infinite repetitions, cosmic bubbles, or mathematical shadows, one thing's clear: the universe we call home might be far stranger, far more crowded than we ever dreamed. And if even one of these theories is true, it means the answer to "are we alone" isn't just yes, it's an infinite, echoing yes. Dark energy isn't just a mysterious force, it's rewriting the cosmic rulebook. In the late 1990s, two separate teams of astronomers made a jaw-dropping discovery while studying distant supernova. These dying stars weren't just moving away from us, they were accelerating, as if some invisible hand were pressing hard on the universe's gas pedal. That revelation earned them the Nobel Prize, and it flipped cosmology upside down. Because here's what it means: the expansion of the universe isn't slowing down as everyone expected. It's speeding up, and the culprit, a shadowy, repulsive force we now call dark energy. This changes everything about the infinite versus finite debate. If dark energy keeps pushing galaxies apart faster and faster, it doesn't just make the universe bigger, it could make the observable universe smaller over time. Picture a frantic game of cosmic hide and seek, where the hiders keep sprinting away faster than you can chase them. Eventually, even the closest galaxies will vanish beyond a horizon of darkness, their light stretched too thin to ever reach us. That's dark energy's cruel twist. It could leave future civilizations peering into an empty void, convinced they're alone in a static, finite cosmos, even if the universe beyond is infinite. Now let's dial up the terror. Enter the Big Rip, one of the most chilling doomsday scenarios in physics. If dark energy's push grows stronger over time, it won't just separate galaxies. Billions of years from now, it could shred stars apart, then planets, then molecules, and finally, in the last fraction of a second, space-time itself might tear at the seams, ripping atoms into non-existence. It's the ultimate cosmic demolition job, where not even the fabric of reality survives. But here's the haunting question: does a Big Rip require an infinite universe, or could it happen in a finite one? The answer lies in dark energy's personality. If it's a constant force, what physicists call a cosmological constant, then even an infinite universe could face a slow, cold death where expansion stretches matter into oblivion. But if dark energy gets stronger over time, as some theories suggest, then the rip becomes inevitable, finite or not. It's like blowing up a balloon with no limit. Eventually, the rubber will give way. What's wild is that we're seeing this unfold in real time. Those Nobel-winning supernova were cosmic canaries in the coal mine, warning us that the universe isn't just expanding, it's losing the brakes. And that acceleration doesn't care about infinity. Whether the cosmos is boundless or just mind-bogglingly big, dark energy is the great equalizer, ensuring that one day, every galaxy outside our local group will be gone, not because they've disappeared, but because space itself is yanking them away faster than light can bridge the gap. So where does that leave us, staring into a future where the universe's true shape might become unknowable? If all evidence of distant galaxies vanishes, how could we ever prove it's infinite? Or finite? Dark energy doesn't just complicate the debate, it might erase the clues entirely. And that's the real cosmic irony. The force that's revealing the universe's expansion could also be the one that hides its ultimate truth from us forever. At the smallest scales imaginable, the universe might not be smooth. It could be a chaotic, frothing sea of quantum foam. Picture space-time itself as an ocean during a storm, with waves and bubbles constantly forming and popping into existence. These aren't ordinary bubbles, they're fluctuations so tiny they operate at the Planck length, a distance so minuscule, it's a million billion times smaller than a proton. This is where gravity and quantum mechanics collide, where the very fabric of reality becomes pixelated like a cosmic digital screen. If space-time has a smallest possible pixel, does that mean infinity is just an illusion? String theory throws another twist into the mix. It suggests that at these unimaginably small scales, the universe isn't just three-dimensional. It's vibrating with extra hidden dimensions, curled up so tightly we'd never notice them. Imagine an ant crawling along a telephone wire. From far away, the wire looks one-dimensional, but up close, the ant can move in circles around its thin surface. Those hidden loops are like string theory's extra dimensions, adding layers of complexity to the quantum foam. So here's the paradox: if space is pixelated at the Planck length but also unspools into higher dimensions, how does infinity fit into the equation? Some physicists argue that a smallest unit of space doesn't necessarily rule out infinity, it just reshapes it. Think of a never-ending staircase where each step is the same size. The steps are discrete, but the staircase itself still infinite. Others counter that if space-time is granular, like a cosmic Lego set, then true smoothness, and by extension true infinity, can't exist. Every measurement, every distance, would just be a whole number of these tiny building blocks. Even the vastness of the cosmos would be countable, like beads on an unfathomably long string. Then there's the wild card, holography. The holographic principle suggests that all the information in a volume of space might actually be encoded on its two-dimensional boundary, like a cosmic QR code. If that's true, then our three-dimensional reality, with all its quantum foam and hidden dimensions, could be a projection. Infinity in this context wouldn't be about endless space, but about infinite information packed onto a surface we can't even see. So, can infinity exist in a pixelated universe? The answer might depend on what kind of infinity we're talking about. A universe with Planck-sized pixels could still stretch forever in extent, even if its resolution has a limit. Or maybe infinity isn't about space at all, but about the boundless complexity hiding within each infinitesimal speck of reality. Either way, one thing's certain: the closer we look, the stranger the universe gets. Here's a puzzle that seems simple at first, but unravels into something profound. If the universe is infinite and filled with endless stars, why isn't the night sky blindingly bright? This is Olbers' paradox, named after 19th-century astronomer Heinrich Olbers, who pointed out the glaring inconsistency in the way we see the cosmos. Think about it. In an infinite universe, every line of sight from Earth should eventually land on a star, like standing in an endless forest where no matter where you look, your gaze meets a tree. The entire night sky should be a solid sheet of starlight, brighter than daylight, and yet it's not. The darkness between the stars isn't just empty, it's a clue to the deepest nature of reality. Olbers himself proposed a clunky solution. Maybe interstellar dust blocks the light, but that doesn't hold up. Over time, all that dust would absorb so much starlight, it would heat up until it glowed just as brightly as the stars themselves. The real answer lies in two game-changing truths about the universe. First, light has a speed limit. It takes time to reach us. Even if space is infinite, we can only see the light that's had enough time to travel here since the Big Bang. That means our observable universe has a boundary not in space but in time. The most distant stars whose light reaches us are messengers from the early cosmos, not the present. Second, and this is where it gets brilliant, the universe isn't static, it's stretching. As space expands, light from distant galaxies gets stretched too, shifting toward the red end of the spectrum. This redshift saps the energy from starlight, dimming it over cosmic distances. Combined with the fact that many stars haven't existed long enough for their light to reach us, this creates pockets of darkness in the sky. It's like running backward on a speeding treadmill. No matter how fast you pump your legs, the belt keeps pulling you away from the finish line. Here's the kicker: Olbers' paradox doesn't just hint that the universe isn't infinite, it reveals that the cosmos had a beginning. A static, eternal universe would have a bright sky. The darkness we see is proof of cosmic evolution, of a universe that's dynamic, expanding, and most importantly finite in age. So the next time you look up at the night sky and marvel at its depth, remember, every pinpoint of light is a time capsule, and every shadow between them is a whisper from the dawn of time. What if the universe isn't just curved, it's folded into an intricate cosmic origami? One of the most mesmerizing possibilities is the Poincaré dodecahedral space, a finite shape where the cosmos wraps around itself like a 12-sided soccer ball. Picture this: light traveling in what seems like a straight line would eventually loop back to its starting point after traversing the universe's folded geometry. The result: ghostly repetitions of galaxies, where a single cluster might appear mirrored in multiple directions like standing in a hall of cosmic mirrors. Astronomers call these ghost galaxies, and spotting them could be the key to proving we live in a dodecahedral universe. The idea isn't just mathematical poetry. Back in 2003, researchers poring over data from the Wilkinson microwave anisotropy probe stumbled on something bizarre. The cosmic microwave background, that echo of the Big Bang, showed strange matchstick-like patterns in its temperature fluctuations. These anomalies were too large and too orderly to be random noise. They fit eerily well with predictions for a universe shaped like a Poincaré dodecahedron, where space's curvature would cause light to take looping paths, superimposing distant hot and cold spots onto one another. It's as if the cosmos were whispering its shape through subtle echoes. But how does this topology actually work? Imagine playing asteroids on an old arcade cabinet, where flying off one edge teleports you to the opposite side. Now replace that flat screen with a dodecahedron's intricate geometry. Light wouldn't just wrap around, it would twist, creating kaleidoscopic repetitions of cosmic structures. If you pointed a telescope in the right direction, you might see the same galaxy cluster appearing in 6 different places, each a ghostly duplicate from light that had circumnavigated the universe. Critics argue the evidence is fuzzy. Later measurements from the Planck satellite softened the original anomalies, leaving the dodecahedral model in limbo. But here's the tantalizing part: even if the universe isn't shaped like a soccer ball, the search for repeating patterns isn't over. Other exotic topologies, like the 3 torus, a universe folded into a hyperdimensional donut, could produce similar ghostly echoes. The challenge: these repetitions would be separated by tens of billions of light years, hiding them just beyond the edge of our observable horizon. What's at stake isn't just a geometry puzzle. A finite, folded universe would rewrite our understanding of reality's scale. No longer would infinity be the default. Instead, we'd live in a cosmos with elegant, looping edges. A cosmic Möbius strip where every journey could, in theory, bring you home. Until we spot those ghostly galaxies or decode deeper anomalies in the cosmic microwave background, the universe's true shape remains one of its most exquisite mysteries. And that's the thrill. The answer might already be written in the sky, waiting for us to decipher its folds. Philosophers have wrestled with the nature of the universe for millennia, and their answers often reveal as much about human imagination as they do about reality. In the East, traditions like Hinduism and Buddhism envision a cosmos that breathes, expanding and contracting in endless cycles. Picture a celestial accordion. Universes rise from the ashes of their predecessors, playing the same cosmic melody across eternity. These cyclical models don't just reject linear time, they dissolve the very idea of a definitive beginning or end. There's no first cause to pinpoint, no final collapse to dread, just an infinite dance of creation and dissolution, where each universe is a verse in an endless poem. Contrast that with the Western tradition, where thinkers like Augustine and Newton saw time as an arrow, a straight path from creation to apocalypse. Here, the universe has a definitive birth. The Big Bang echoes this notion, a middle and an inevitable end. It's a narrative with stakes, where infinity isn't a given but a question mark. Immanuel Kant encapsulated this tension brilliantly in his Antinomies, pairs of logical but contradictory conclusions about space and time. On one hand, he argued, the universe must have a beginning, or else an infinite chain of events would have needed to pass before now, an absurdity. On the other, it can't have a beginning because what existed before that? Both answers defy intuition, leaving us trapped in what Kant called the embarrassment of reason. This divide isn't just academic, it shapes how we grapple with existence itself. In a cyclical cosmos, meaning might come from recurrence, every life, every star, every atom destined to replay its role in the grand script, but in a linear, finite universe. Suddenly, every choice feels weightier, every moment more fragile. Existentialists like Sartre saw infinity as a kind of terror. If space and time have no edges, how do we anchor our significance? Are we just flickers in an endless void, or does our very questioning of infinity hint at something deeper? Modern cosmology hasn't settled this debate, it's amplified it. The multiverse theory, with its infinite branching realities, mirrors Eastern cyclicity in its vastness. Yet the heat death of the universe, a slow fade into cold, eternal stillness, feels eerily aligned with Western linearity. Perhaps the real revelation is this: whether the universe is infinite or finite, cyclical or linear, our struggle to comprehend it reveals a truth not about the cosmos but about us. We're creatures who crave edges even as we're mesmerized by the boundless, and that tension between the finite and the infinite might be the most human thing of all. Mathematics gives us two flavors of infinity, and they're as different as water and fire. The first, countable infinity, is familiar, the endless march of whole numbers, 1, 2, 3, stretching toward a horizon that never arrives. It's the infinity of a child counting stars, where each point of light gets a number, even if the task itself is endless. But the second kind, uncountable infinity, is where things get unsettling. Think of every possible point along a line segment, every microscopic speck between 0 and 1. No matter how finely you slice it, there's always another number, another fraction, another decimal place waiting to be named. This isn't just more, it's a denser, stranger infinity, one that can't be neatly listed or ordered. The man who unraveled this mystery, Georg Cantor, paid a heavy price for his discovery. In the late 19th century, he proved that some infinities are bigger than others, a revelation so radical it shattered mathematical conventions and, some say, his sanity. Imagine stepping into a library where every book is a unique infinity. Some are thin volumes with numbered pages, others are bottomless wells of unreadable text. That was Cantor's vision, an infinite hierarchy of infinities, each more vast than the last. The strain of this cosmic truth haunted him. He suffered debilitating depression, writing letters to philosophers and theologians, desperate to reconcile his math with the divine. In the end, he died in a mental asylum, his genius a warning about the toll of staring too long into the abyss. Now fast forward to modern cosmology. If Cantor's infinities exist in math, could the universe embody them too? One camp argues space is a smooth continuum, an uncountable infinity where distances can be divided infinitely, like a line stretching forever. But others propose a wild alternative. The cosmos might be a fractal, a self-repeating pattern where the same structures appear at every scale. Picture zooming into a galaxy cluster and finding tiny galaxies shaped like the larger ones ad infinitum. If true, space wouldn't be a featureless expanse, it'd be a Russian nesting doll of infinities, each layer a perfect echo of the whole. Here's where physics collides with philosophy. If the universe is fractal-like, does that mean it's built from countable infinities, discrete, repeating units? Or does it still hide the uncountable chaos Cantor uncovered? Some theorists suggest spacetime itself might be pixelated at the Planck scale, a cosmic grid where here and there blur into quantum foam. Others argue that even if space is granular, its potential states, the way particles arrange themselves, might still form an uncountable set, an endless variety too rich to catalogue. The implications are dizzying. A fractal cosmos could mean we're living inside a mathematical artifact, a structure so finely detailed it mirrors itself across scales. A continuum universe, that's the realm where black holes hide singularities, points of infinite density, and dark energy stretches spacetime like taffy. Either way, infinity isn't just a concept out there. It's woven into the fabric of reality, shaping everything from the spin of electrons to the fate of galaxies. And perhaps that's the ultimate takeaway. The universe doesn't just contain infinities. It is one whether we're ready to count it or not. What if the universe isn't just finite or infinite? What if it's rendered? That's the unnerving question at the heart of simulation theory, where the debate over cosmic boundaries collides with the possibility we're living inside an artificial construct. Think of it like this: even if our universe feels infinite, could it just be an illusion crafted by unfathomably advanced code? Elon Musk famously put the odds at 1 in billions that we're living in base reality, arguing it's more statistically likely we're digital ancestors in some civilization's hyper-realistic simulation. And if that's true, the very idea of infinity might just be a clever trick, a sleight of hand by the programmers. Procedural generation offers a fascinating clue. Modern video games use this technique to create vast, seemingly endless worlds without storing every pixel in memory. Take a game like No Man's Sky, where algorithms generate planets on the fly as players explore, each one unique but only real when observed. Now scale that up to universal proportions. A simulated cosmos could mimic infinity by generating galaxies and quantum fluctuations only when we look, saving computational power by leaving the rest in a fog of mathematical potential. It's like a cosmic version of the tree falling in the forest thought experiment. If no one's there to measure it, does a distant star even exist? But here's where physics throws a wrench in the simulation argument. If our universe is a construct, it would need to run on some substrate, a hardware of sorts, and no matter how advanced, all computing faces limits. Even simulating a finite universe atom by atom would require more energy than exists in that universe. That's why some theorists propose a cheat. The simulation might not render everything in perfect detail. Instead, it could approximate, like a video game, lowering resolution in the distance. Oddly enough, quantum mechanics hints at something similar. Particles don't have definite properties until measured, as if reality is optimizing processing power by only resolving what's observed. Yet not everyone's convinced. Critics argue that positing a simulation just kicks the can down the road. Who created the simulators? If their universe is infinite, we're back to square one. If finite, what created them? It's turtles all the way down. Others point out that glitches, evidence of the simulation, should surface if the code isn't flawless. So far, the universe's laws appear consistent, with no cosmic blue screen of death. Perhaps the most haunting implication isn't about infinity at all, but meaning. If we're living in a simulation, does it matter whether the universe is truly infinite? Or is the question itself just part of the script? The irony is delicious. We might never know if we're pondering genuine cosmic truths or following lines of code designed to make us wonder. Either way, one thing's certain: the simulation argument doesn't simplify the mystery of existence. It deepens it, turning the night sky into the ultimate uncanny valley. Time itself might be the deepest mystery of all. Did it have a starting gun, or has it always been ticking? The Big Bang Theory suggests a definitive beginning, a singularity where both space and time ignited into existence. Picture a cosmic hourglass with all the universe's matter and energy squeezed into a single, inconceivably dense point at the bottom. Flip it over and time begins its relentless flow. But here's the catch: asking what happened before the Big Bang might be like asking what's north of the North Pole. If time didn't exist, there was no before. Yet that answer feels unsatisfying, like a magician's trick where the rabbit vanishes but no one explains how. Enter Roger Penrose, the Nobel Prize-winning physicist who dares to imagine time without end. His conformal cyclic cosmology paints a universe not with one big bang but countless rebirths. Imagine the cosmos as a phoenix. Instead of dying in heat, death, or collapse, it sheds its entropy, its chaos, through the evaporation of black holes. In Penrose's vision, these black holes, over near infinite stretches of time, radiate away their energy, leaving space-time smooth and featureless. At this point, the universe forgets its own scale. A universe stretched to infinity and one shrunk to a singularity become mathematically identical, and in that moment of perfect symmetry, the cycle resets. A new Big Bang ignites not from a singularity, but from the ashes of the previous eon. The audacity of this idea lies in its evidence. Penrose claims to have found echoes of past eons imprinted on the cosmic microwave background, circular patterns he calls Hawking points, theorized to be the ghostly signatures of ancient black holes from a universe long gone. Critics dismiss these as statistical flukes, but if true, they'd rewrite time's arrow entirely. No longer a one-way street from birth to oblivion, but a Möbius strip where each end loops into a new beginning. Yet the cyclic model isn't the only challenger to time's singularity. Some quantum gravity theories suggest the Big Bang wasn't a true beginning, but a bounce, a prior universe collapsing until quantum effects reversed its implosion like a rubber band snapping back. Others propose time isn't linear at all, but a branching tree where every quantum decision spawns new timelines. What's striking is how each theory reshapes our place in the cosmos. A universe with a definitive start implies a narrative, an Act 1 where we're latecomers in a story already 13.8 billion years deep, but an eternal cycle. That's a cosmic rhythm where every ending seeds a new dawn. Whether time is finite or boundless, one thing's certain: our clocks are just whispers in a conversation that may have no first word and no last. Black holes aren't just cosmic vacuum cleaners, they're the ultimate paradox, places where the universe folds in on itself and the rulebook of physics gets shredded. At their heart lies the singularity, a point of infinite density where gravity becomes so strong that space and time cease to behave in any recognizable way. Imagine crushing the entire mass of a star or even a galaxy into a speck smaller than an atom. The equations of general relativity scream in protest here, spitting out nonsensical answers like infinite curvature and zero volume. It's as if the cosmos is flashing a bright red warning sign. Beyond this point, reality as we know it ends, but here's where things get even weirder. The holographic principle, born from the fiery debates over black hole physics, suggests that all the information swallowed by a black hole isn't lost forever. It's smeared across its event horizon like cosmic graffiti. Picture a black hole not as a pit of destruction, but as a two-dimensional projector screen encoding the three-dimensional drama unfolding inside. This idea, championed by physicists like Leonard Susskind, flips the script on infinity. If the singularity is a mathematical impossibility, a place where physics breaks down, the holographic principle offers a workaround. Maybe infinity is just an illusion, a glitch in how we perceive the deeper, pixelated structure of reality. Pop culture loves to romanticize these cosmic enigmas. Take Interstellar's Gargantua, a black hole rendered with such scientific precision that physicist Kip Thorne won a Nobel Prize for the research it inspired. The film's depiction of the singularity, a shimmering, fractured tesseract where time becomes a physical dimension, is pure Hollywood, but it captures a kernel of truth. Black holes do warp time so severely that minutes near one could equate to years elsewhere. And while we'll never see a lone astronaut surviving a plunge into the void, Gargantua's portrayal of space-time as a navigable landscape isn't entirely fantasy. It's a poetic nod to the idea that black holes aren't just dead ends, they're puzzles begging to be solved. So which is it? Are singularities truly infinite abysses, or are they finite structures wearing infinity as a disguise? The answer might lie in the tension between two competing visions of reality. Einstein's relativity paints a universe of smooth, continuous fabric where singularities are inevitable. But quantum mechanics whispers a different story, one where information can't be destroyed and even black holes must play by the rules. Until we find a theory that reconciles these two giants, black holes will remain the universe's ultimate riddle, cosmic sirens luring us toward the edge of understanding, only to vanish into the dark when we get too close. String theory's vision of the universe is like nothing you've ever imagined. It suggests that reality isn't just the three dimensions we experience: height, width, and depth, but a tapestry woven from at least 10, maybe even 11. So where are all these extra dimensions hiding? According to theorists, they're curled up into shapes so tiny, so intricate, that they evade detection, geometric masterpieces called Calabi-Yau manifolds. Picture a garden hose. From far away, it looks like a simple one-dimensional line. But up close, you realize it's a tube, a two-dimensional surface wrapped into a circle. Calabi-Yau manifolds take this idea to cosmic extremes, folding 6 or 7 extra dimensions into structures so complex, their geometry determines the fundamental laws of physics in our visible universe. The vibrational patterns of strings dancing through these shapes could explain why electrons have their specific mass, why gravity is so weak compared to other forces, even why the universe has the exact structure it does. Brian Greene paints a breathtaking portrait of this idea in The Elegant Universe, where he describes these manifolds as the hidden architecture of reality. The optimism is infectious. If we could just map the exact Calabi-Yau shape our universe's extra dimensions are curled into, we might unlock a theory of everything. But there's a catch. Despite decades of searching, no experiment has detected even a whisper of these extra dimensions. The energy scales required to probe them are so far beyond our current particle accelerators, it's like trying to hear a pin drop in a hurricane. Critics argue this makes string theory less science and more philosophy, a beautiful mathematical daydream with no anchor in observable reality. Now here's where infinity creeps back in. If these extra dimensions exist, could they harbor their own nested layers of endlessness? Imagine a universe where every point in our familiar 3D space contains a tiny, coiled-up infinity, a fractal of dimensions within dimensions. It's a dizzying thought, but the math allows for it. Some string theorists speculate that Calabi-Yau manifolds might not just be static shapes, but dynamic, fluctuating entities with their own subdimensions, like Russian dolls made of pure geometry. In this scenario, higher dimensional infinity wouldn't just mean space stretching forever. It'd mean infinities tucked inside every quark, every photon, like cosmic origami folding endlessly inward. Yet for all its elegance, string theory remains a castle in the clouds. Without experimental proof, it's hard to shake the nagging question: are we describing the universe or just the limits of our imagination? Greene's optimism is a rallying cry for patience, a bet that future technology will unveil these hidden layers. But until then, the extra dimensions of string theory linger in a quantum superposition of their own, both infinitely possible and, for now, frustratingly out of reach. Cosmic inflation is the universe's ultimate magic trick. A fraction of a second after the Big Bang, space itself exploded outward faster than light, stretching a speck smaller than an atom into a cosmos vast enough to seed all the galaxies we see today. But inflation isn't just about size, it's the key to solving two of the universe's greatest mysteries. First, the horizon problem. Why does the cosmic microwave background, the afterglow of the Big Bang, look so eerily uniform in every direction? Without inflation, patches of the sky separated by billions of light years could never have reached the same temperature, like two strangers on opposite sides of the planet wearing identical outfits without ever meeting. Inflation fixes this by suggesting everything we see was once crammed into a tiny, ultra-connected region that got stretched smooth, like pulling taffy until all the lumps vanish. Then there's the flatness problem. The universe's geometry is so perfectly balanced between open and closed that it's like a pencil standing on its tip for billions of years without falling. Inflation explains this by blowing up space so dramatically that any initial curvature became negligible, just as inflating a balloon makes its surface appear flatter and flatter from the perspective of an ant crawling on it. Alan Guth, the physicist who pioneered inflation theory, called it the ultimate free lunch, a fleeting moment where gravity itself became repulsive, converting quantum jitters into a staggering expanse of spacetime. And the meal ticket, the energy driving inflation, might have come from a peculiar state of vacuum energy, meaning the universe could have literally expanded from nothing. But the wildest twist is eternal inflation, where the process doesn't stop everywhere at once. Picture a pot of boiling water. Most regions cool into the universe we know, but some bubbles keep boiling forever, spawning new universes like foam in a never-ending cascade. In this scenario, our cosmos might be just one bubble in an infinite multiverse, each with its own laws of physics. Some bubbles could be lifeless voids, others might crackle with exotic particles we can't even imagine. And because these bubbles are born endlessly, the multiverse becomes a fractal of realities, some finite, some infinite, all born from that same explosive stretching of spacetime. Here's the kicker: if inflation is true, the observable universe is just a speck in a far grander picture. The entire cosmos could be more than 10 to the power of 23 times larger than what we can see, a number so vast writing it out would fill thousands of books. That's the humbling beauty of inflation. It doesn't just explain the universe's smoothness and flatness. It suggests we're living in a cosmic grain of sand on an endless beach, where the tides of spacetime never stop rolling in. If life is the universe's way of observing itself, does that mean reality had to be built just right for us to exist? That's the heart of the anthropic principle, an idea so simple, it flips the cosmic debate on its head. Brandon Carter, the physicist who coined the term, put it bluntly: we observe the universe because we're here to see it. In other words, the mere fact that we're having this conversation means the universe must have properties that allow life to emerge. It's like a puddle waking up one day and marveling at how perfectly the hole it sits in fits its shape. But here's the twist: does that perfect fit require a finite cosmos with finely tuned constants, or could life thrive just as easily in an infinite reality where every possible condition exists somewhere? Think of Earth's Goldilocks zone, that narrow band around a star where water stays liquid, not too hot or cold. Now scale that up to the entire universe. If the laws of physics were even slightly different, if gravity was stronger, electrons heavier, or the cosmic expansion rate tweaked by a fraction, atoms wouldn't bond, stars wouldn't ignite, and life as we know it would be impossible. That precision has led some scientists to argue the universe must be finite, because an infinite cosmos would dilute those perfect conditions into statistical noise. In a truly boundless reality, why wouldn't life be vanishingly rare, lost in an endless sea of dead space? Yet supporters of infinity fire back with a counterintuitive punchline: life isn't the miracle, it's the inevitability. If the universe is infinite, then every possible combination of physical constants exists somewhere. We don't live in the one universe fine-tuned for life. We live in the only slice of the multiverse where observers could arise to ask the question. It's like winning the cosmic lottery, but in a sea of infinite tickets someone had to win. The stakes here aren't just academic. If the universe is finite and fine-tuned, it whispers of something deeper. A designer, a multiverse generator, or a yet unknown physics that locks our constants in place. But if it's infinite, then life is just a fleeting spark in an eternal storm, one of countless flickers in the dark. Carter's principle doesn't pick sides, it just reminds us that the answer, whatever it is, must explain why we're here to ponder it. And that's the real magic. The universe isn't just a place, it's a mirror reflecting back the very conditions that let it be seen. Imagine peering through a telescope so powerful it could spot the faint echoes of universes that came before ours, or maybe even catch a glimpse of our cosmos looping back on itself. That's the promise of next-generation observatories like the James Webb Space Telescope and the upcoming LISA mission. These aren't just upgrades, they're game changers designed to hunt for clues that could finally crack the universe's ultimate riddles. Take topology, for instance. If space is folded into some exotic shape, a dodecahedron, a torus, these instruments might detect the telltale repetitions of galaxies or anomalies in gravitational waves that hint at cosmic origami. LISA, a space-based gravitational wave detector, could catch ripples from colliding black holes that reveal the hidden geometry of spacetime itself, like listening for echoes in a hall of mirrors. Then there's the hunt for neutrino masses, ghostly particles so lightweight they barely interact with matter. Why do they matter? Because their exact mass could tip the scales in the curvature debate. If neutrinos are heavy enough, they'd exert a gravitational pull that subtly warps the universe's geometry. Pin that down, and we might finally know whether space is flat, closed, or something even stranger. It's like using a feather to measure the tilt of a mountain, a delicate clue with cosmic implications. But the real showstopper, the possibility of multiverse signatures. If our universe collided with another in the distant past, the shockwaves might still linger in the cosmic microwave background, like bruises from a long-forgotten cosmic fistfight. Future telescopes could scan for these scars, testing whether we're alone in reality or just one bubble in an infinite foam. Will 2050 finally answer whether the universe is infinite? Maybe we'll uncover deeper layers to the mystery, like peeling an onion with no center. One thing's certain, the telescopes of tomorrow aren't just tools, they're time machines built to decode the universe's best-kept secrets. And what they find could rewrite not just textbooks, but our very place in the grand scheme of things. Science fiction has always been a playground for the infinite, from the cosmic musings of Isaac Asimov to the flashy spectacle of the Marvel Cinematic Universe. Take Asimov's The Last Question, a short story where humanity's quest to reverse entropy spans trillions of years, ultimately revealing a universe that collapses and rebirths itself. A mind-bending twist on cyclical cosmology. Here, infinity isn't just a backdrop, it's the punchline, a revelation that ties the story's philosophical weight to real theories like conformal cyclic cosmology. Compare that to Marvel's Ant-Man and the Wasp, where the quantum realm is tossed around as a catch-all for time travel, alternate dimensions, and universe-breaking power-ups. The problem, it treats infinity like a narrative band-aid. Need a way to undo Thanos' snap, just slap quantum on it and call it science. Hollywood's love affair with infinite universes often sacrifices accuracy for spectacle. Films like Doctor Strange in the Multiverse of Madness delight in kaleidoscopic alternate realities, but reduce the multiverse to a funhouse mirror of cameos and Easter eggs. Lost in the CGI fireworks is any nod to the rigorous physics underpinning these ideas, no mention of eternal inflation, bubble universes, or the fine-tuning problem. Even Everything Everywhere All at Once, for all its brilliance, leans into the absurdity of infinite selves rather than grappling with the existential weight of a truly endless cosmos. It's entertaining, sure, but it leaves audiences thinking the multiverse is just a chaotic dice roll, not a frontier of cutting-edge cosmology. Yet not all pop culture gets it wrong. Neil deGrasse Tyson's Cosmos stands out for its commitment to grounding grandeur in real science. When it tackles the universe's scale, it doesn't just wow you with zoom-out animations. It explains the cosmic microwave background, the redshift of distant galaxies, and the very real math behind whether space is flat or curved. And then there's Interstellar, where Kip Thorne's involvement ensured the black hole Gargantua wasn't just a pretty void but a scientifically plausible warping of space-time, accretion disk and all. These works prove you don't have to dumb down infinity to make it captivating. You just have to respect the audience enough to let them glimpse the real wonder beneath the fiction. The irony, sci-fi's missteps reveal something profound about our relationship with infinity. We're drawn to it as a concept, the ultimate what if, but struggle to reconcile its mathematical coldness with our hunger for narrative closure. Maybe that's why so many stories bend infinity into a tool for resurrection, revenge, or redemption. It's easier to face the endless dark when it's got a superhero in it. But the best depictions, like Asimov's or Cosmos, remind us that the true awe of infinity lies not in how we weaponize it, but in how it dwarfs us, challenges us, and ultimately connects us to the cosmos in ways deeper than any script could capture. Staring into the abyss of an infinite universe can trigger two equally profound but opposite reactions. One whispers that humanity is cosmically insignificant, a fleeting flicker in an endless void where trillions of civilizations might rise and fall without ever crossing paths. The other insists we're rarefied miracles, our existence balancing on a knife's edge of physics so precise it borders on impossible. This tension between nihilism and awe isn't just philosophical, it's deeply human, forcing us to confront what meaning looks like against the backdrop of eternity. Take the nihilist's view first. In a truly infinite cosmos, every possible version of you exists somewhere alongside infinite versions that never drew breath. If the universe has no edges, no end to its repetitions, then our triumphs and tragedies aren't just small, they're statistically inevitable. Like grains of sand on an endless beach, individuality dissolves into the vastness. Philosopher Friedrich Nietzsche captured this terror when he wrote about the eternal return, the idea that every moment recurs infinitely. Would you live the same life over and over, knowing nothing you do ultimately matters? But then there's Carl Sagan's pale blue dot perspective. When Voyager snapped that iconic photo of Earth from 4 billion miles away, a speck suspended in a sunbeam, Sagan didn't see insignificance. He saw fragility worth cherishing. Every human who ever lived, every joy and suffering played out on a mote of dust, he reflected. In an infinite universe, the absence of cosmic specialness doesn't erase meaning, it relocates it. Meaning isn't handed down from the stars, it's built here in the choices we make, the connections we forge. The sheer improbability of our existence against the cosmic odds becomes the reason to treasure it. Here's where science throws a curveball. If the universe is infinite but life is vanishingly rare, a statistical fluke in a sea of lifeless voids, then humanity isn't just precious, we might be the universe's only chance to know itself. Astronomer Jill Tarter, who spent decades hunting for extraterrestrial signals, calls this the Great Silence. The more we search and find nothing, the heavier that silence grows. Suddenly, our pale blue dot isn't just one voice in a cosmic chorus. It might be the only voice singing alone in the dark. Yet even if we're not alone, even if infinite civilizations hum across the void, that doesn't diminish our story, it enriches it. Picture a library with infinite books. Does knowing other volumes exist make the one in your hands less valuable? Or does it remind you that every page, every word is part of something grander? The ethical takeaway isn't despair or arrogance, it's responsibility. In a cosmos that might stretch forever, our choices ripple further than we'll ever see. An infinite universe doesn't erase meaning, it asks us to create our own, and that's the most human act of all. Even among the brightest minds in cosmology, the question of infinity sparks fiery debate, none more heated than between Sean Carroll and Laura Mersini-Horton. Carroll, a vocal advocate for the infinite universe model, argues from a bedrock of mathematical elegance. To him, infinity isn't just plausible, it's the universe's default setting. He points to quantum field theory, where particles flicker in and out of existence endlessly, and to the flat geometry of spacetime revealed by cosmic microwave background data. An infinite universe isn't a stretch, he insists. It's the simplest solution that fits the equations without needing extra assumptions. For Carroll, infinity is the ultimate Occam's razor. no edges to explain, no boundaries to justify, just an endless cosmic tapestry where every possible quantum fluctuation plays out somewhere. Mercini Horton, on the other hand, isn't buying it. Her work in quantum gravity suggests a finite cosmos, one where the very fabric of spacetime has a calculable limit. She's famous for her bold claim that black holes can't form, a direct challenge to Einstein's relativity, and she brings that same rigor to the infinity debate. At a 2023 cosmology conference, she clashed with Carroll over anomalies in the cosmic microwave background. If the universe were truly infinite, she countered, we'd see statistical uniformity in the CMB. Instead, we're finding cold spots and asymmetries that suggest a finite, self-contained structure. Her vision, a universe shaped like a quantum bubble, its boundaries defined by the same physics that birthed it. The tension between these two camps crystallized last year when new data from the Atacama Cosmology Telescope revealed bizarre, large-scale fluctuations in the CMB. Carroll's team interpreted them as random noise in an infinite cosmic sea, while Mercini Horton's group saw fingerprints of a finite topology, a universe that might even curve back on itself. The debate got so intense, one observer joked it was less a scientific discussion and more a heavyweight title match. So where does that leave us? Carroll's infinite universe offers a grand, almost poetic vision, a cosmos without end, where every possibility blooms eternally. Mercini Horton's finite model feels more intimate, like a cosmic snow globe where every particle, every galaxy, is part of a closed, knowable whole. Both arguments hinge on the same data but spin it into wildly different stories. The beauty is, you don't need a PhD to have an opinion. Look up at the night sky tonight. Do you see an endless frontier or a vast but bounded mystery? Your answer might say more about you than the universe. After this cosmic journey, we're left balancing on a razor's edge between the universe's breathtaking scale and its haunting mysteries. The cosmic microwave background whispers one story, a flat, infinite expanse where galaxies stretch into forever. Yet those strange anomalies, cold spots, asymmetries hint at folds in the fabric, a universe that might curve back on itself like an Escher drawing. Then there's dark energy, that shadowy force stretching spacetime faster than light can chase it, erasing clues before we can decode them. Will future civilizations peer into an empty sky, their questions swallowed by the void? Philosophy steps in where physics falters. Infinity isn't just a number, it's a mirror reflecting our deepest fears and fascinations. The ancient Greeks saw eternity in the stars. Nietzsche trembled at eternal recurrence. Today, we measure cosmic flatness down to a fraction of a percent, yet still can't say for certain whether we're floating in an ocean without shores or a vast but bounded pond. Here's the beautiful paradox. Our uncertainty doesn't diminish the wonder, it deepens it. Whether finite or infinite, the universe has spared no expense in dazzling us. Superclusters spin like cosmic hurricanes, black holes warp time into pretzels, quantum foam dances beneath our fingertips, and we, temporary, fragile, impossibly lucky, get to witness it. So tonight, step outside, look up, those pinpricks of light. They're either the first notes of an endless symphony or the dazzling finale of a one-time show. The answer changes everything and nothing, because right now, in this fleeting moment, the universe is asking you, which version feels true? Hit subscribe and let's keep chasing the answer together.